In the Andes of South America, engineers were forced to carve roads straight into cliffs that drop for hundreds of feet. One small mistake could have sent entire crews and machines into deep ravines. Yet they pushed forward with precise measurements, controlled blasts, and equipment weighing hundreds of tons balanced on narrow ledges. The result is a network of roads that wrap around the mountains like tight threads, reconnecting places that had been cut off for centuries, and the technique behind it is far more intense than it looks. Building roads on the edge of a mountain. One clear example of a road cut straight into a cliff is an old mountain route in Bolivia called Yungas Road. It links the high city of La Paz with a lower, greener region called the Yungas, and for much of its length it is little more than a narrow strip of dirt sitting on the edge of a huge drop. In some places the road is only about 10 feet wide, with trucks and buses squeezing past each other while 1,000-foot cliffs fall away just beyond the tires. For many years, this roughly 40-mile stretch was known as one of the most dangerous roads in the world, with an estimated 200 to 300 deaths annually during its most dangerous years before a safer bypass opened in 2006. Roads like this are not only found in Bolivia. In the western United States, a section of United States Highway 550 in Colorado, often called the Million-Dollar Highway, has a similar feel, with steep slopes, sharp curves, and places where drivers run close to the edge with no guardrails while snow, ice, and falling rocks remain constant threats in winter. In both South America and North America, the basic problem is the same. People need a way across the mountains, but the mountains do not offer much flat ground to build on. At high altitudes, there is less oxygen in the air, so engines make less power and workers tire more quickly. Weather also changes faster at these heights. Clear sun can turn to fog, heavy rain, or snow in a short time, and that makes both driving and building far more risky. On top of that, the rocks are often broken and unstable, so storms and earthquakes can shake loose blocks and send them crashing down onto whatever sits below. Cutting a road into a cliff starts with choosing a path that the mountain will accept. Engineers study maps, aerial photos, and satellite images. Today, they use drones and laser scans to build three-dimensional models, spotting old landslides and unstable slopes. They avoid the weakest areas while keeping the route short enough and gentle enough for trucks to climb. Survey teams then transfer the planned route from the map to the mountainside using GPS, marking the center line with paint and flags. Looking up at the cliff, you might see a thin stripe of bright markings showing where the road will go. With the line marked, the real cutting can begin. Crews use drilling machines to push steel rods into the rock along the marked line. These drill holes are set out in neat rows and patterns with known spacing and depth, so that the rock will break in a controlled way. Workers then load each hole with small amounts of explosive, along with plugs that help direct the blast. Instead of firing all the charges at once, they use timed detonators so that each hole fires a tiny fraction of a second after the one next to it. This makes the rock break and fall in the right direction without shaking the entire slope. These blasts are carefully planned so they peel off a slice of rock that matches the planned shape of the road bench, which is the flat shelf that the road will sit on. In places where homes or other roads lie below the work area, crews hang curtains made of heavy mesh, old tires, or special fabric to catch flying pieces of stone. The goal is always the same: break just enough rock to make a flat ledge, and do it without damaging anything that needs to stay standing. Once the dust has settled after a blast, excavators move onto the fresh pile of broken rock. Their metal buckets bite into the loose stone and load it into trucks that crawl along temporary tracks on the new ledge. These trucks carry the waste rock to planned disposal areas. Sometimes the material is used to build up low spots along the road or to create small embankments. Other times it is tipped into special dumps placed so that even if the pile slides a little in the future, it will not bury the road or nearby homes. Blast by blast, cut by cut, the bare cliff slowly gains a continuous shelf. As the rough shelf grows longer, machines switch from breaking rock to shaping it. Bulldozers push remaining piles of rubble toward the outside edge and spread the material more evenly. Then graders, which have a long blade hanging under the middle of the machine, move back and forth, shaving off high spots and filling shallow dips. The goal is to reach the planned width and slope so that the shelf is just a little higher on the inside next to the rock wall and slightly lower toward the edge. This gentle tilt helps rainwater run toward a ditch or drain instead of soaking straight into the mountain or pooling on the roadway. A solid road needs more than a shaped rock shelf. Once the rough shape is right, crews build up the road structure in layers. If the exposed rock is weak, crews strip it away and replace it with better stone. Then they spread layers of crushed rock, compacting each with heavy rollers until it's dense enough to carry traffic. While all this is happening underfoot, another crew is looking up instead of down. These workers focus on the cliff above the new shelf. They move along the face with ropes, harnesses and safety lines so that a slip will not send them falling. With steel bars and small hammers, they tap the rock and listen for hollow sounds that might mean a block is loose behind a thin crust. When they find such blocks, they pry them off while the ledge below is kept clear. This careful work removes many of the pieces that might otherwise crash onto the road during storms or during freeze and thaw cycles. In areas where the rock is badly cracked or weathered, simple scaling with bars is not enough. There, crews install extra supports. They drill long holes into the face and glue or grout steel rods deep into stronger rock behind the surface. These hidden bars act like pins that hold the outer skin of the cliff in place. On some sections, they spray a coat of wet concrete onto the face. This sprayed concrete, often called shotcrete, hardens into a thin shell that binds loose fragments together and shields the cliff from rain and ice. Over wide stretches, they hang steel wire mesh, pinned at the top and sides, so that small stones that do break free slide down behind the mesh, instead of bouncing across the roadway. After the shelf is shaped, the base layers are strong, and the cliff above is secured. The crews turn the gray stone surface into a smooth, dark strip. They begin by spraying a thin coat of liquid asphalt onto the compacted stone. This tack coat acts like glue between the base and the new surface layer. A paving machine then crawls along the route while trucks back up and dump hot asphalt mix into its hopper. Inside the machine, the mix is spread out and leveled by a heated plate so that it comes out the back as a flat layer. Workers with rakes stand on both sides of the machine and pull asphalt into corners, along the edge of the rock wall, and around tight curves where the machine cannot spread it perfectly on its own. Right behind the paver, large rollers move in overlapping passes, squeezing the hot mix into a dense, smooth surface before it cools and hardens. Once the asphalt has cooled, crews sweep off loose grains and then add paint lines where there is enough width and set up posts or barriers wherever there is room to do so without making winter snow clearing impossible. A famous example of this type of mountain road in the United States is the Going to the Sun Road in Glacier National Park in Montana. This route is a little over 50 miles long and crosses the Continental Divide at Logan Pass at an elevation of more than 6,600 feet. About 12 miles of the road were literally carved into steep rock walls, with stone guard walls on the outside edge and almost no flat ground beyond that. Construction began in the early 1920s and was finished in the early 1930s, and at the time, it was seen as one of the most difficult and beautiful mountain roads ever built in a national park. But carving a shelf only works when the rock is stable. When the cliff is too broken or the slope too unstable, engineers stop cutting into the mountain and start building outward into empty air. The wild engineering behind hanging roads. On California's Big Sur coast, there is a short stretch of Highway 1 where the ground under the road kept sliding toward the Pacific. For years, massive slides repeatedly closed this section, sometimes for over a year at a time. Engineers finally accepted that cutting the cliff back any farther would only make things worse. Instead of shaving more rock away, they decided to step out into empty space and carry the road on a bridge that hugs the side of the slope, held up by strong concrete supports anchored deep into the hillside. That basic problem shows up in mountain ranges all over the world. When workers remove too much material from the base of a slope or cut into layers that are already broken and wet, the rock above can start to move, especially during heavy rain or earthquakes. When the rock sends that clear warning, the idea flips. Instead of cutting farther into the slope to make a ledge, engineers keep the cliff mostly as it is and build new support out from it. The road is no longer sitting on a bench carved into the mountain. It hangs on columns and a deck that stand partly in mid-air. You can think of it as wrapping a thin balcony around the side of the mountain. with each post drilled and locked into solid rock so the whole structure carries its own weight instead of depending on a fragile wall of soil. These hanging roads show up under many different names: columns, piers, viaducts, cliffside bridges, but the basic idea is the same. The first step is to decide exactly where each column should stand. Designers pick a line for the road that clears the worst rock above, but still allows drivers to follow the side of the mountain without sharp, dangerous turns. Survey teams then mark the future column spots on the slope, often in places where the rock is strongest. On a route like Highway 1, some of those supports had to sit on very steep ground that drops hundreds of feet to the sea. So crews built small concrete pads or pedestals stepped into the hillside to give each support a firm base. At Pitkin's Curve, for example, California's Highway Department realigned approximately 1,700 feet of road and added a short bridge on columns plus a rock shed to carry traffic past a cliff that had been sliding for decades. To anchor each support, drilling rigs bite down into the rock and cut deep holes that reach stable layers well below the loose surface. Workers lower cages of steel bars into these holes and then fill them with concrete, creating hidden roots that tie the column to the mountain. Once the foundations cure, crews pour the visible shafts, one lift at a time, until the tops reach the height of the planned road. On slopes with big drops, those shafts can rise well over 100 feet above the ground, so the builders work from temporary platforms, with safety lines clipped to the structure the whole time. In some mountain projects, the columns start near the valley floor. In others, like parts of the Big Sur coast, they stand on shelves cut into the cliff, so the bridge can swing around a problem area without dropping all the way down. Once there is a forest of solid columns in place, the next challenge is to build the actual roadway on top without spending years working on a dangerous cliff. This is where prefabricated deck pieces come in. Instead of shaping the entire bridge on site, engineers cast many short pieces of the road in a safer area, under factory-like conditions. Each piece is a thick concrete slab with steel inside, shaped so it fits neatly against the next one. On famous cliffside bridges in the United States, these pieces are often only around 8 or 9 feet long, but they can weigh about 50 tons each, so every move has to be planned. The Lynn Cove Viaduct on the Blue Ridge Parkway in North Carolina is a classic example of how this works when engineers want to protect both drivers and the mountain. The bridge is about 1,243 feet long and wraps around the side of Grandfather Mountain on just 7 concrete supports. It was built as the last missing link of the parkway in the late 1970s and early 1980s. To avoid tearing up a very fragile slope below, the crew did almost all of the work from the top. They cast 153 separate concrete segments near the site, each about 8½ feet long and around 50 tons in weight, then fed them one by one to a special crane that crawled along the growing bridge. Each piece was set in place, glued to its neighbor with strong epoxy, and locked together with steel cables inside. That same build-from-above approach is now common on many mountain viaducts. Sometimes a big launch machine sits on top of the last finished span and reaches out to grab the next segment. On shorter jobs, a tower crane or a crane on a nearby ledge can do the lifting. Workers stand on the deck, guide each heavy block into position with tag lines, and line it up until the joints match. Once a few pieces are set, workers run steel tendons through holes inside the concrete and pull them tight with jacks. When the cables tighten, they press the pieces together so strongly that the whole line acts like one solid beam. This approach, called segmental construction, is used a lot because it lets crews finish faster on dangerous slopes and creates less noise, dust, and traffic. Once the structure is in place, the road surface itself is more familiar. Crews put a concrete slab or base layer on top of the girders, add a waterproof layer, and then lay asphalt or concrete for the driving surface. A road on the side of a cliff still has to handle tight curves, steep slopes, snow, ice, and heavy rain, so engineers focus a lot on drainage and traction. On the Lynn Cove Viaduct, for example, the bridge had to twist around sharp curves and rise and fall while still feeling smooth to drivers. The structure was tuned very carefully, and decades later it is still performing well with no major structural problems reported by the Park Service. Holding a road in midair is not just about weight. Engineers have to design for trucks braking hard on downhill curves, strong side winds that push tall vehicles, and earthquakes that shake the whole system from below. In places like coastal California and the Andes, bridges sit in regions where earthquakes can trigger landslides and damage supports. Bridge codes there require designers to check how much the columns and decks will move during strong shaking, and to add details that help the structure flex without failing. California's Highway Department, for example, has its own seismic design rules, and research on precast segmental bridges has focused on making sure that joints and columns can rock and then settle back into place after a big quake. All of this has to stay safe for decades, not just on opening day. That is why the road deck has drains to carry water away before it can leak into joints or wash out soil near the bases. Expansion joints at the ends of spans let the bridge grow and shrink with temperature without cracking. Bearings between the deck and the tops of columns allow just enough movement during heat cycles or small quakes. Over time, inspectors check for rust on steel, small cracks in concrete, or changes in how the bridge moves under traffic. If something looks off, they can add more anchors, wrap columns with extra material, or replace pieces before a minor issue becomes a major one. Working on these structures during construction is its own challenge. Crews often stand hundreds of feet above a canyon floor or above the ocean, with only a guardrail and a safety line between them and a long fall. They move along temporary walkways bolted to the side of the deck, connect their harnesses to lifelines, and communicate with crane operators by radio and hand signals, especially when wind and engine noise make it hard to hear. On the Big Sur coast today, at Regent Slide, California has even started using remote-controlled bulldozers and excavators to move dirt on unstable slopes so that operators can stay back in a safe trailer while machines work near the edge. There is also a clear environmental and community reason to choose columns and viaducts over deeper cuts. A hanging road can cross a sensitive slope while leaving most of the soil and plants in place underneath. That matters in parks and protected areas, where wildlife needs space to move and where bare scars on the mountain would last for generations. On Grandfather Mountain, the Lynn Cove Viaduct was chosen specifically to protect rare plants and fragile rock, and it has become a textbook case of how to thread a road through difficult terrain without wrecking it. For people who live in these mountains, the result is simple but life-changing. A narrow dirt track that once closed for weeks after every storm can be replaced by a stable, elevated road that stays open far more often. Farmers can get crops to markets, kids can reach schools, and ambulances do not have to gamble on cliff edges that are always one rainstorm away from collapse. The upfront cost of columns, deep foundations, and prefabricated decks is high, but the payoff comes in fewer long closures and less constant repair work on slopes that never really wanted a road carved into them in the first place. Carrying a highway on columns along the face of a cliff is one of the boldest tricks in the mountain road toolkit. But there are still mountains where even a hanging road is not enough, where rockfall, snow, or ice make the outside of the slope too dangerous all year round. In those stretches, the only safe way to keep traffic moving is to leave the cliff alone and hide the road inside the rock itself. Carving roads through solid mountains. On the border between Chile and Argentina, the route between Santiago and Mendoza once climbed a high pass with long switchbacks exposed to snow and strong wind. Today, most traffic uses the Cristo Redentor Road Tunnel, a little under 2 miles long at about 10,500 feet above sea level. The tunnel, opened in 1980, avoids the most fragile ridge that was often closed by winter storms and now carries trucks and cars all year. Farther north, the planned Agua Negra Tunnel would add 2 parallel road tubes, each almost 8.5 miles long, under another Andean ridge. The Argentine portal would sit above 13,300 feet, turning a harsh, storm-prone pass into a protected link meant to cut travel time for freight to Pacific ports. Both projects show why, in some mountains, the safest place for a road is no longer on the cliff at all, but hidden inside solid rock. Building a road inside a mountain starts with air, not rock. Deep underground, smoke and exhaust from engines cannot simply drift away. If air does not move, dust and gases build up until people cannot breathe. During construction, engineers drill 1 or more shafts from the tunnel up to the surface. These shafts can be almost vertical or gently sloping, but their job is simple. Fresh air comes in, and dirty air goes out. Many deep shafts are made with a method called raise boring, where a small pilot hole is drilled first, and then a larger cutting head is pulled back through the rock to open a full-size shaft without putting people at the bottom. In Taiwan's Suishan Road Tunnel, which is about 8 miles long, 3 sets of vertical shafts were built, with the deepest reaching approximately 1,450 feet into solid rock. Once a tunnel is open and carrying traffic, fresh air is usually moved along the roadway by powerful fans mounted in the roof. These are often called jet fans. Each fan blows a strong stream of air along the tunnel, and the moving stream pulls the rest of the air with it. Several fans spaced along the ceiling can push exhaust toward the exit and bring in clean air from the other end. For many road tunnels, this longitudinal system is used because it is simple, reliable, and easier to maintain than large duct systems. To keep people safe, the air system is tied to sensors that watch what is happening inside the tunnel. Fixed gas detectors on the walls or ceiling constantly sample the air for carbon monoxide and nitrogen oxides, which are toxic gases produced by engines. A European standard called EN 505451 sets rules for how such detectors should perform in car parks and tunnels, including how they should react when gas levels rise. Control systems use these readings to automatically start or speed up fans if exhaust builds up during slow or stopped traffic. Fire is the other major risk. A burning truck in a tunnel can reach very high temperatures and fill the space with smoke in minutes if nothing is done. To plan for this, designers follow rules such as NFPA 502, a standard that covers fire protection for road tunnels, bridges, and limited access highways. These rules guide the choice of fire-resistant linings, emergency exits, and fixed firefighting systems such as sprinkler or water mist lines mounted in the roof. Fire systems and ventilation work together so that during a fire, fans push smoke away from trapped drivers and hold a cleaner layer of air low over the road to help people escape. All of that support system only matters if a tunnel can be driven through the mountain in the first place. In the past, long road tunnels were made by drilling and blasting short sections at a time. That method is still used on smaller jobs, but the biggest modern tunnels use huge tunnel boring machines, often called TBMs. A TBM is like a moving factory that eats rock at the front and leaves a finished tunnel behind it. Some of these machines are longer than a 30-story building laid on its side and weigh several thousand tons. Before a TBM can start to cut, it has to be assembled in a large underground chamber at the start of the tunnel. The machine arrives in many heavy pieces on trucks or construction trains. Crews build a strong concrete floor and walls, then use cranes and lifting gear to set the front cutting head, the main shield, and the long train of support decks behind it. Laser instruments line the whole machine up with the planned path of the tunnel so that, as it moves, it stays within a few fractions of an inch of the center line drawn by the designers. The front of the TBM is a round steel plate with many disc cutters on it. Each disc is a thick steel wheel that is pressed against the rock with very high force. As the cutting head turns, the discs crack the rock in front into chips. The broken rock falls into openings in the head and onto a belt or screw conveyor. From there, it rides on more conveyor belts or small trains back out of the tunnel to big piles on the surface. At the same time, jacks at the back of the cutting head push against the tunnel lining or against the bare rock to shove the whole machine forward a short distance. Then the jacks pull back, new tunnel segments are set, and the cycle starts again. To show the scale, it helps to look at a few record breakers. In Switzerland, the Gotthard-based tunnel runs for about 35 miles under the Alps. 4 large TBMs, each about 1,400 feet long and weighing around 3,300 tons, helped dig the twin tubes. At its deepest point, the rock roof is more than 7,500 feet above the tunnel, yet trains now pass through that solid mountain in about 20 minutes. In the United States, the State Route 99 tunnel under downtown Seattle was bored by a TBM nicknamed Bertha. The machine was about 57.5 feet wide, roughly 326 feet long, and weighed several thousand tons. Bertha broke down just 1,000 feet into the tunnel in December 2013 after hitting a steel pipe, requiring nearly 2 years of repairs before boring could resume. It dug a 2-mile-long double-deck highway tunnel about 200 feet below the streets, allowing an old waterfront viaduct to be removed. Traffic now runs on 2 levels inside the tube, with space below for ventilation equipment and other systems. As the cutting head advances, crews behind it build the permanent shell of the tunnel. Instead of leaving bare rock, they place curved concrete panels called segments around the inside of the opening. Each segment is precast in a factory with steel inside for strength. A full ring often needs 6 or more of these pieces. Workers set the segments with small cranes, bolt them together, and install rubber seals in the joints so that water cannot leak through. Then the narrow space between the outside of the concrete ring and the rough rock is filled with grout, a thin cement mix that locks everything in place. Once the tunnel reaches daylight at the far end, the noisy part of the work is over. But the road is not ready yet. Engineers and builders move through carefully, checking each ring of the lining for cracks, chips, or leaks. Small defects are fixed with repair mortars and sealants. Drains are cut along the sides and in the center, so that water running down from the rock can be collected and pumped away instead of pooling on the roadway. Concrete walkways are cast along the walls to give people a safe path if they ever have to leave their vehicles in an emergency. The tunnel is then filled with systems that most drivers never notice. Cable racks and ducts carry power, phone lines, and data. Lamps on the ceiling keep light levels even so that drivers' eyes can adjust when they enter and leave. Cameras watch traffic and send live pictures to control rooms. Emergency phones, fire hose cabinets, and bright signs mark safe areas and exits. In the State Route 99 tunnel, for example, there are 15 refuge spaces spaced along the tunnel, each with an escape route behind a protected door leading to the ends of the tunnel. More than 300 cameras feed back to a traffic center that can close the tunnel, reverse fans, or call in help within seconds. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.